Hello and welcome back. It's me again, Miss Dixon, and we are exploring counting methods today all together. Now, this is something that some of you may have seen a little bit of during Units 1 and 2, but the reason we're going back over it now is to make sure you've got a really solid understanding and you know exactly what's going on so that you're all ready for when we need to use these techniques in the probability and statistics section of the course, which is the last area of study we will cover. Now, a lot of this hopefully will make some logical sense to you, and as we go through, the concepts may get a little more difficult. As a new incentive this time, if I make any mistakes and you're the first person to spot it and let me know, I will give you some kind of tasty, delicious prize. Hopefully I don't make any mistakes, but if you do spot them, come and let me know. So let's get started. Sorry, there we go. Okay. We are starting by talking about the addition rule. Now, this is something that is a pretty basic concept, to be honest. What we're saying is that if we have to choose between different alternatives, we need to add up the number of choices available for each alternative. So this is where we're looking for the word or. This is the key word that we're focusing on in this case. We're essentially just saying how many options there are. Notice at the moment, when we're doing counting methods, we're not working out probabilities, okay? So when we're talking about counting methods, that's our topic right now. It is not the same as, not equivalent to probability. Counting methods is a useful tool, but it's not the same thing. We're not actually working out the chance of things happening. We're just seeing how many options there are. So, here we have Sandy can't decide whether to wear a wind cheater or a jacket. Okay, she has a look in her closet. She has 4 wind cheaters, or jumpers you might call them, and 2 jackets. So because we're trying to decide whether she wears a wind cheater or a jacket, we're using the word or here. Do notice I do concede the point that yes, it might say and over here. But what we're actually talking about is what she's going to wear. She's going to wear a wind cheater or a jacket. She is not going to wear a wind cheater and a jacket in this case. It's one or the other. So when she goes to put something on, she has 4 choices from wind cheaters plus 2 choices from jackets. So altogether she has 6 choices of what she will wear on the top of her body. Pretty straightforward, I hope. Moving on to the multiplication rule. So in this case, this is when we've got sequential choices, okay? So we're looking at sequential choices. The total number of possibilities is found by multiplying the number of options at each stage. So if there's m choices for the first stage and n choices for the second stage, then we multiply them together. And generally we're looking for the word and this is something that would have came up in your probability studies in the past. So we're back with Sandy again. Let me just change colour for a second. Okay. She has 6 choices of wind cheaters or jackets. 6 choices or wind cheaters or jackets, okay? So with her first choice, what she's going to wear, I'm just going to call it her tops here because these are things that she's going to wear on the top half of her body. She has 6 options. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Yes, good, I can count. Okay. And she has 7 choices of jeans or skirts. So I'm going to, just for the sake of convenience, call these the bottoms. Now people, something at the top of their body and something on the bottom. So she's gone for one of these 6 choices for what to wear at the top. Once she's chosen that, she then has 7 choices. Whoops. 7 choices. 1, 2, 3, 4, 5, 6, 7 choices coming off from here. Okay? She has 7 choices of the bottoms there. Once she's got her, if she chose the second top, she would have another 7 choices. Following on from this one, another 7, another 7, another 7, and another 7. What we're saying is that if we're counting the ends of the branches of this tree diagram, if we're trying to figure out how many branches we end up with, we are going to have 6 multiplied by 7 options, because we have 6 branches in our first part here, and then each of those have 7 branches coming off them. So altogether, how many choices does she have for a complete outfit? She will have 42 choices. And so that is the multiplication rule. Notice that we're looking for the word "and" in this case. She's going to wear a jumper or a jumper or a wind cheater, so we added here, and so we're multiplying a jeans or a jacket, so we're adding there. Okay, so keep that in mind. Let's go on to things getting a little more difficult. Okay, now that we've continued on, we start talking about something called arrangements. They also get called permutations. Okay, either word is fine. So when we're talking about an arrangement, it's something where the order is important. So when we're talking about the arrangements in this example here, A, B, C and C, B, A are different. If we're wanting to find how many different ways I could rearrange the letters A, B and C, we could do it by listing them out. So I could start with A and then have B and C, or I could start with A followed by C and then B. Okay? Or I could start with B, my A and my C, or B, C, A, or I could have C, A, B, or C, B, A. So in this case, we have 6 different possibilities. So that's relatively easy. The problem comes when we have many more objects or items that have to be arranged, and it starts to get really difficult and really confusing to figure this out. So we need to have easier ways of sorting out, easier ways of figuring out exactly what's going on. One way that we can do this is by considering how many spots we have, how many places. I have 3 positions, okay? For this first position here, if we are assuming, because we're arranging these 3 letters in any order, that no letter may be repeated, when I'm choosing which one to put in the first box, I have 3 choices. I have the choice of A, B or C. I have 3 choices. When I go to figure out which letter I can put in my second box, one of these has been taken. I don't know which one yet, but one of them has been used, and I now only have 2 choices for my second letter. Again, another one has been taken, and that means I only have 1 choice for my final option. So this means that to work out how many options we have 3 times 2 times 1, we have 6 possible arrangements. There are 6 ways of arranging the letters A, B, C, okay, which is the same as what we got up here, but we can see that we can use this formula easier. How we represent this, if we have a pattern like this, 3 times 2 times 1, decreasing consecutive numbers, this is the same as saying 3 factorial. Whoops. 3 factorial. Okay. And our factorial formula, we can see, is this one over here. N factorial equals n times n minus 1 times n minus 2, and so on. So this is an important formula to use, and I will show you a little bit later how we use this formula and how we type it into our calculator. Now we're going to hold off on the second part, on our second formula here. We're going to come back to this a little bit later on. So let's move to examples. So we're wanting to see, okay, how many ways are there of arranging 4 different books on a shelf? So if we construct our shelf here, construct a little grid, we can divide this into 4 because we're going to have 4 positions for our 4 books. For my first book, I have 4 choices. I can put any of my 4 books in the first position. Once I've put my first book here, in the second spot, I now only have 3 books to choose from, so I have 3 choices. I now only have 2 books left, so I've got 2 choices. And in the final spot, I've only got 1 book left, so I must put it in that position there. That means that I have 4 options, and then 3, and then 2, and then 1. So that means the way we work this out is by saying 4 factorial. This little exclamation point in maths means factorial, and that is equal to 4 times 3 times 2 times 1. Okay, and we can work this out. So there are 24 different ways of arranging 4 books on the shelf. And hopefully you can see that working it out this way is much more easy and simpler rather than actually listing all of the options. Okay, our next example. We now have a painter and they're going to paint the 5 circles of the Olympic flag, but he can't remember the colours to use for any of the circles. He knows they should all be different. So we've got 5 circles. So we have 5 choices, and even though they're circles, I'm still going to draw it in a little grid like this. So we have 1, 2, 3, 4, 5 options. He knows they should all be different. Okay, he has 8 colours of paint available. So that means the first choice, he has 8 choices for which circle to paint the first one. He paints that one because they're going to be different. The second circle, he now has 7 colour choices, and then 6, and then 5, and then 4. So we can work this out. 8 times 7 times 6 times 5 times 4. And you can just put that in your calculator and type it in, and what you get is 6,720. Please don't trust me. Go and type it in your calculator yourself. What we want to know though, is there a formula? Because if we start writing this out for really large numbers, we could be here typing into our calculator for a really long time. Having a formula of some kind would be useful. Well, what we want to do, let me choose another colour. What we want to do is to somehow write this as instead 8 factorial, okay? Now 8 factorial is equal to, if we take what we had before, 8 times 7 times 6 times 5 times 4, that's what we already had, that's what we had to work out our answer. But to get 8 factorial, because that would be a nice part of our formula, we also have to multiply by 3, by 2, by 1. But what I'm wanting is to achieve just this part here because I want it to be equal to 6,720. If I multiply by 3, by 2, by 1, I should also divide by 3, by 2, by 1. Now when we look, hopefully you can all agree that this first expression here is going to be identical to this second expression we've got right here. And if you don't believe me, type it into your calculator and check. We should be getting the same value. Which means what we're getting is in the numerator we have 8 factorial because I've multiplied 8 by 7 by 6 descending consecutive numbers all the way to 1, divided by, in the numerator, I have 3 factorial. Our question now becomes, where does this 3 actually come from? And here's where it comes from. We had 8 choices to start with, and we had 1, 2, 3, 4, 5 spots. So where this has come from, and sorry about all of my colour changing, I was trying to find something nice but it's not really working for me, is that our numerator is 8 factorial. Our denominator, the way we've got that is that we took our 8, our number of colours that we had in this case, our 8 colours, and we subtracted 5 which was our number of circles we had, our 5 circles, and that's how we got our 3. And this is actually our formula. The way that it is written is in terms of P, because we're doing permutations. So the way that we write this is that we say NPR, that's our notation, is equal to, and our formula is that we have n factorial divided by n minus r factorial. Okay, this is the formula that we are going to use. So this is it. This is our formula that we can use to work out how many possible arrangements there are, or permutations, that's what the P stands for, given some different criteria. So n is the number of items or objects that we have. In this case, that's colours. And R is the number of items that we select. So how many colours do we need? So in this case, we had 8 colours, so that was our n, 8 objects, but we were only selecting 5 colours, so our number of items selected is only 5, and that's our R value. Okay, if we wanted to put this into our calculator, what do we do? So we're looking at putting this 9PR in this case. So we had 8 factorial, we have this formula here, and what we're saying there, so this is what we're going to look up, is that we are going to put into our calculator the choice of, in this case, n is 8, p, how many permutations we can have, 8 colours that have been, our permutations, our arrangements, 5 of them to be selected. So calculator, where we find this, within the main menu in the keyboard, we need to go to the advanced section, and here we can see factorial. So earlier on we worked out 4 factorial, so let's just put that in for a second. 4 factorial gives us 24, which we know it should. And right now what we're doing is that we wanted to use this PR. Now we actually click it first, and then we type our n value, which in this case was 8, comma, our R value, how many of those, so we had 8 colours, how many colours are we choosing? We're going to be choosing and arranging 5 of them. We close the bracket, press execute, and we get our same number again, 6,720. So like I mentioned, when we put it in our calculator, we once again get 6,720. Let's do a couple of other examples before we move on. Okay, so in this case, we want to find the number of different 4-digit numbers that can be formed from the digits 1, 2, 3, 4, 5, 6, 7, 8, 9 if each digit can be used only once. If we're using our formula from before, we're using each only once, okay, and that's what we need to use our formula. When we're using this permutation button function of our calculator, it only works if we're using each option once. So in this case, our value of n, how many choices do we have? We have 9 different choices, 9 different numbers. How many of them are we going to select? Our R value, we're going to select 4 of them. So our formula will be n, will be n, C, oh, not C. Okay, so our formula in this case that we're doing, we've got 9 options. How many permutations or arrangements can we get? We're going to be arranging 4 of them. And if we go to our calculator now, okay, so our choice this time, we're doing our permutations. We have got 9 different numbers. We are selecting 4 of them. So we have 3,024. Notice that if we decided we wanted to do this our other way, We could use our factorial button as well, because our other way of doing it is that we say 9 factorial divided by n minus r. Okay, n minus r is 5 factorial. And notice that we get the same answer. Okay, so we have our answer here, which is 3024. If you, instead of using the formula, wanted to do it using the positions, that will of course work as well. We have 4 positions, we have 9 choices in our first spot, 8 choices in our second, and then 7 and then 6. And if we work out 9 times 8 times 7 times 6, you will get the same answer again. Now our second option is different because our numbers can be used more than once. So if we think this time about our choices, within our first box, in our first position, we have 9 different possible numbers that we could put in. Because our numbers can be used more than once, in our second slot, we again have 9 options. In our third slot, we have 9 options. And we have 9 in our fourth as well. So when we're using our numbers more than once, we can't actually use that nice formula. Our answer will just be 9 times 9 times 9 times 9, or 9 to the power of 4. And we can put that in our calculator to work out our answer. And it should make sense to everyone that when we've got, when our numbers can be used more than once, we're of course getting many more possible arrangements, possibilities, than when our numbers could only be used once, as in the previous part. The final example for this one that we're looking at is how many different even, this is our keyword, even 4-digit numbers can be formed. In this case, if we are looking for specific conditions that have been applied, we actually need to use our method of placing our values. We can't use the nice formula in this case either. So we have, I'm sorry, some of my squares are getting a little small there. If our value has to be even, then that means our last number can only be a 2, a 4, a 6, or an 8. That's the only way to get an even number. So we have 4 choices. Then when I go, because each digit may be used only once, this is the next important part. Alright, when I choose this value here, well, whichever one I've used there is missing. So instead of having 1, 2, 3, 4, 5, 6, 7 options, like I had initially here, I don't have 7, oh sorry, I forgot number 1 up here. Okay, instead of having 8 options, I now actually only have 7, because one of the numbers was one of the 4 that went in this position down here. I've now put 2 of my numbers in out of my 8. 2 of my numbers out of the 8 have had positions, so I only have 6 left. Now 3 of my numbers out of the 8 have been put in, I have 5 left. Notice it doesn't matter where I put the 7, 6 and 5. 7 times 6 is the same as 6 times 7. It doesn't matter which boxes we fill, but we get the same numbers anyway, and we can work this out. We can put it in our calculator to figure out that there are 840 different possible 4-digit even numbers formed from those digits. Now, I forgot to say early on, feel free to pause as you're going and answer some of the practice questions yourselves, or if you'd like, continue on to our last concept for today. So we're now looking at selections or combinations instead. Now the difference between this and the other is that in this case the order is not important. So earlier on we were saying that A, B, C and C, B, A were different. That's what we were saying previously when we were talking about arrangements. When we're selecting things, we don't care what order they're selected in, just what they are. That's like if I was selecting, if I was putting my hand into a prize jar and pulling out 3 prizes, it wouldn't matter which order I get them in because I'll get to keep them all anyway. It just matters what they are. So that's when we're talking about selections. If we are selecting people who will attend a particular excursion, it doesn't matter which order your name was selected because you will still be attending. So that's when we're talking about selections. The order doesn't matter. If we think back to this option here, if I had the 3 letters A, B and C, and I wanted to think in how many ways I could select 2-letter combinations, okay? 2-letter combinations. Well, if I care about the arrangement, I could have A and AB, or BA, or I could have AC or CA, or we could have BC or CB. If we're wondering about arrangements, I have 6 options. But if I'm just talking about combinations, how many combinations are possible, I have only 3. These first 2 are the same. They are both the case where the letters A and B have been selected. This next one is the case where the letters A and C have been selected, and the last where the letters B and C have been selected. So how many arrangements would be possible? There would be 6 arrangements, but there are only 3 selections or 3 combinations. So when we're doing this, knowing the number of distinct selections of objects might help us to determine the number of elements in the sample space. We want a formula to do this in, and we're going to talk about where this formula here comes from. Because what we don't want is to have to work this out all of the time. It's exhausting if we have to list them all. We need a more efficient way. So here is our formula, NCR. So in this case, the C stands for the combinations that we're looking at here. So let me try to choose a good colour. I don't know. Let's see how this orangey one looks. So if we're looking at our formula, N, the same as what we were talking about before, N stands for the number of objects, okay, or people or items, the number of objects that we have in total. R is the number of objects, R is the number of objects we select. So in our example over here that we had, in our option there, we had 3 objects, we had 3 letters, and we were going to combine 2 of them. So we had 3 possibilities and we wanted to select 2 of them. So how we work this out? What we're saying is that we work out NPR to start with. So NPR, this is all possible arrangements. We say, okay, let's work out all possible arrangements. How many arrangements can we possibly get? In our option over here, we had 1, 2, 3, 4, 5, 6 arrangements. But that's not the same as how many combinations. So to figure out how many combinations, we work out R factorial. So what we're doing here is that we are saying, what is the number of ways our objects can rearrange themselves? And in this case, our R factorial, our R value was 2. So 2 factorial, 2 times 1. How many ways can these objects rearrange themselves? Well, here we had 2 options, A and B, and there was 2 possibilities. It could be this first option or it could be this second one. There is 2 ways these items, these objects, the objects A and B, could rearrange themselves, and that's how we get our answer of 3. When we put this formula together, this part here is the NPR part, and we also have this R factorial part here, which is coming in when we're trying to work out our combinations. Once again, NCR can be found on our calculators. Let's do a couple of examples, shall we? All right, so we have 4 flavors of ice cream. This is how many choices there are, how many objects or items. They're available at the school canteen. Very nice canteen. How many different double scoop selections are possible if 2 different flavors must be used? Now in this case, we're saying order doesn't matter. This is the key thing to look for. Does order matter or does it not? In this case, order doesn't matter because I don't care if I had my lovely looking ice cream scoop here. I'm saying it does not matter which of these ones is chocolate. If it's chocolate down here or if it's chocolate up there, I don't mind as long as I get 2 different colours. Sorry, not colours, 2 different flavours. Order doesn't matter. So we're looking at combinations rather than permutations. So we have 4 flavours. So it's going to be 4. We're combining 2 different ones. We've got 4 flavours. We're combining 2 different ones. Let's go and look at how to do it on the calc. Okay, once again we're in the advanced menu. So just to remind you, we have to click down here, our advanced menu, and this time we're doing NCR because we're combining options. We have 4 different ice cream flavours and we are choosing 2 of them. Sometimes we can think of the C as standing for choosing. How many are we choosing? It doesn't matter in which order. And we have 6 possibilities. So 4 choose 2, that equals 6. So there are 6 different possible double scoop selections. We could have tried it with listing. If we were listing, we would have had our vanilla and then our, we could have had vanilla and then chocolate, or vanilla and strawberry, or vanilla and caramel. Or we could have had chocolate. Now chocolate and vanilla is the same as vanilla and chocolate. So we could have had chocolate and strawberry, or chocolate and caramel, or strawberry and caramel. So again, we've got 6 different options. We can see it by listing as well, but listing really can be tricky, especially if we look at some of the bigger ones. So let's look at this one here. We have a team of 3 boys and 3 girls is to be chosen from a group of 8 boys and 5 girls. Now I've got 2 different parts here. So a team of 3 boys to be chosen from a group of 8 boys. And again, order does not matter. I do not care which order the boys were chosen in. So I have 8 boys and I need to choose 3 of them. And I also need to choose 3 girls. So I'm choosing again, but this time I've got 5 girls and I'm going to choose 3 of them. Because we said the word and, that's what we're doing. We're choosing 3 boys and 3 girls. I multiply. This first part here is going to tell me how many boys, how many choices there are, how many ways I can select 3 boys from 8 boys, how many different possibilities. This different value over here is going to tell me how many different ways I can select 3 girls from the 5. Multiplying those together, because we need 3 boys and 3 girls, we will get our total number. So let's put this into the calculator. So we're wanting, in this case, remember we type our NCR first, and we're wanting to have we've got 8 boys, we need to select 3 of them, and we get 56. So there are 56 ways we can select those 3 boys, and we've got 5 girls, and we want to select 3 of them. So our total answer would be 560. Of course, you can type this in straight away if you would like. Oops, sorry. I need the multiply sign, which is hard for me to get to, so I'll just use this for now. We could type this all together and get our answer straight away, 560. So our option is, when we work this out, we ended up with 560. This is how many different teams are possible. Quite a lot if you think about it. Okay, everybody, that is all that we need to know about counting methods. Notice we haven't actually worked out any probabilities in this case. We've just considered counting. We're considering how many different ways things can happen, how many different options there are. This is something that you will need to use down the track when we get up to our final area of study looking at probability and statistics. If I made any mistakes, make sure you let me know. As I said, first one to do so gets an edible prize. Otherwise, if you have any questions, please write them down somewhere. Make sure you come and ask next term. Enjoy your holidays, and thank you for listening.